Great. Okay, so now we are live for the YouTube as well. So how about we start reviewing what we did last time? So we talked about big O, and we gave you the formulas for big O, and we gave you like the examples of what big O is, right? So if we scroll up here, we said that f of n is equal to O, that's big O of g of n as n goes to infinity when f of n is less than or equal to a constant m times g of n for all n that are greater than the given n0, which you give. Oh, I see that. Good point. Thank you for that. I know why that's the case. It's because I opened Canvas. I screwed it up. There we go. So let me fix that again. Okay, we're good then. Great. Thank you. Thanks for that. So as I was saying, big O is going to be your f of n is equal to big O of g of n. So some function f of n is equal to big O of g of n as n goes to infinity. N is the number of operations. When f of n is less than or equal to some constant m times g of n for all n that are greater than n is 0, that n0 is some number you pick. And that's going to be kind of like from here on. And the reason you pick that number is because like in the beginning, things might be a little wobbly before they stabilize, or like an algorithm might be slower in the beginning, but overall it's better off and whatnot, right? So that was big O. Big omega was the same thing, but you just flip the sign. You say that f of n is greater than or equal to m times g of n for all n greater than n0. And the reason why f of n has to be bigger is because you want the real function to be always above the given g of n function, because you want that to be beneath it because it's a lower bound. And on the other hand, when you're doing big O, you want the one above it to be the one you're giving, and f of n to always be less than that one. So that is why this is less. You know, the test has open notes, so I mean, you don't have to memorize these things, but it's very easy still to accidentally flip the sign. So make sure that you don't flip the sign if you're asked on a test to define big O or something like that. And then big data is a combination of both of those, and I show you how that's actually the case. Now you have two constants. Change the letter from m to k just because we call them k1 and k2, but it's the same thing. It's just a combination. It's that really tight bounding. And then I started to give you examples of time complexities that you use. We got logarithmic, we got linear, quadratic, cubic, quartic, and I was just talking with a friend who took 302 a couple of semesters ago, and now he's taking the algorithm analysis class, which is kind of like the sequel to this class. And he gave a name which I wasn't aware of, but I guess it's legit. And it's for this one. Remember I said this n log n is kind of like a special one that you also have? There's actually a name for that one. It's called linearithmic. And I was like, is that a real thing or was that made up? And we searched it on Wikipedia and it's like a real thing. So I'll put it in there as well. Okay, so that's linearithmic time. And normally, if you have something like 2n, 3n, or even if you have a time complexity like this in here that says n squared log n, like that is not its own time complexity. We just kind of say that's just n squared, whatever. You kind of just simplify it in that sense. But this one with the n log n is so special because of sorting that it became its own thing. And now I guess it has its own name too. So. Yep, it's good to know, and it comes back in 477, so might as well tell it to you. And by the way, they did teach you the word cubic in that class over the tertiary thing we were thinking about. So we triple confirm that it's cubic. Okay, and then you have your exponential time. So literally all this stuff is what they're talking about in 477. So that class, a lot of it should be reviewed from this class, and also reinforcement. So even if now you're iffy with the stuff, you'll see it again. Whether that's a good thing or a bad thing, it's up to you. But I'd say it's a good thing because you reinforce it. It might be bad if you hate it and you're like, oh no, I have to see this again. So, yep, indeed, confirmed. I did mention the word heuristics very briefly. I said that like these exponential time stuff is really bad, but there is a way around that with heuristics, which is basically an educated guess using a computer. But really, again, that's something more you would see in 477 or maybe at the end of class if you have time. And then we started looking at code, and that's kind of where we left off. We said, okay, we know these time complexities. Now, can we actually like look at code and figure what the time complexity is of that, at least estimated, within that big O range. Okay. We have a question. What if the exponent was n plus 1? Would it still be exponential? Yes. So anything in any range where this exponent right here is what changes will be exponential. So whether it's n plus 1, or even if you do n squared up here, by the way, if you say like n squared here, which by the way, we'll talk about logarithms today and what happens in this scenario. But even if you do something like that, it's still considered exponential, whereas this stuff is polynomial. So anyways, yeah, so we started looking at code, and then and we're like, okay, let's figure out some examples, and we did like really easy ones. We said, okay, let's just make a loop that just runs from 0 to n and see how long that takes. And you guys said linear time, and I said very good. And then we did nested loops, and we said, okay, what if we have two loops nested with each other? They'll go from 0 to n each, and you turn out to guess correctly that indeed, when they are nested, you basically multiply the time complexities of each individual loop. So it becomes n times n. And then, we didn't do an example of that, but we can do very quickly what happens if you have a loop inside a loop inside a loop. So like three nests basically. So something like if we have this, and then like, here actually, to make it easier, let's just make the outer loop. So if I say like for int, let's just say k equal to 0, k less than n, k plus plus. And then I guess I'll need curly brackets technically, because this whole for loop is like one statement. So then all you do is you add that extra n. So then it becomes n times n times n. So it becomes that cubic thing, right? So same thing. You get the pattern, right? And then we looked at not nested loops, but loops that are running one after the other. So sequential loops. And it turns out that in that scenario, you add the numbers together, or you add the n's together. So instead of being n times n, it becomes n plus n, which does indeed become 2n. Which we can just say is just n. Again, you just simplify it. In fact, there is this idea of a certificate, which I do want to talk about. Certificate. That what you basically say is, well, okay, your constant or your m is going to be equal to 2, and then your n has to be greater than 1 for this to be true. And then you can provide an n 0, but we don't really provide that. But in this case, it would just be 0. So then you would say, okay, if somebody asks you like, okay, can you explain to me why this belongs to this? And the way you write that mathematically is you can say O of 2n is an element of O of n. That's what this means, this little euro, like it looks like a euro symbol. What that means is element of. And so the proof for that is saying, well, if you remember what the big O definition says, we say that we have m times some g of n, and all we're saying is this m is equal to 2. Okay? So that is kind of like your proof as to why we can simplify this here, because it's just a constant. Okay? But anyways, then I copied and pasted the same stuff again twice. That's why that's there. So yeah, that's pretty much where we pick up. And so I have a couple of other examples to do that would lead us into logarithms, right? So this is where things get a little trickier. So I kind of hinted with the word logarithm in there, but what if I give you this function? What is this going to be? Anyone have any guesses? And if you do guess, you have to explain why that's the case for this one. Just because, yes, you are correct, indeed that is logarithmic time, but why? Like that's the tricky part of this one. Like the other ones are obvious what they're linear, but this one, like it feels like why? What here makes it that logarithmic? The index is increasing in terms of a base. I like that. I like that explanation much better. So yes, because every time you increase here, it's like you're multiplying times 2. So yes, it becomes a base like an exponent. So then you get 2 to the first, 2 to the second, 2 to the third. So essentially, if you're kind of making a formula to this, it becomes 2 to the I. And so 2 to the I is going to kind of jump into this logarithm world because it's increasing not linearly, but now it's going in these bigger exponential steps. So it turns out that it is indeed logarithmic. So this is O log of n. Okay, now I'm going to explain to you how you can go from here to here in a second when I show you the log rules. But this is one example that actually came from a homework assignment for 477, by the way. So take note of that if you end up getting the same question. And this is what yesterday introduce it because the student that took through 2 with me was like, hey, I remember the stuff from your class, but I don't remember how to answer this. And he came to me and said, okay, what is the time complexity of this one? This one above it here. So, does anyone have any guesses as to what the time complexity of this one is? So someone's saying it's O constant. So I wouldn't say that. I would flat out say it's O of 0 the way it's written. Right? Because 0 times 2 is 0. Yeah, so it's always 0. So I guess you could say 0 is a constant, but yeah, it technically here is just going to be O of 0, which is kind of weird because it means it's instant. So yeah, I would not put O of 0 and O of constant in the same category, but I guess you theoretically could. So I mean, in a way, when you say O of C, maybe, but it's kind of, I would put it separately, to be safe. Okay, very good. Now let's make one tiny change. Actually, here, let me leave that. Let me leave this here so that we have all examples. That's why I put some space up here. So now let's just leave that here. And then make this say O of 0, so you all know. Because remember, at some point I might share you like this PDF, so you can have this for like the final or something. Okay, so let's make a change now. This is where things will get actually really confusing. O of 1. So okay, so no longer we have that 0 situation, because now it's going to be 2. When I is equal to 1, this is basically the next time from there it's going to go to 2. And then from there, it's going to go to 4. So we still have that 2 to the I concept. However, oh, I forgot to add something to this now. Let's go ahead and change this to not just be n, but to be n squared, which I'm just going to rewrite as n times n. But in his homework, they actually put it as n squared, which was weird. It was trippy. I was like, whoa, 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 that's trippy. But technically, they didn't say it was C++ code. But yeah, let's do this now. So what is the time complexity of this now? And this one's tricky, by the way. I don't expect you to like immediately guess this. So someone's saying O square root of n. It's close. That's close. I was going to talk to that a little bit later, but it does turn out that indeed, when you look at a time complexity of O of log n, it turns out that it is equal to O of square root of n. These two are equal because of something about the logarithms that I'll talk about, which is the base of logarithms. But so yeah, I mean, you are actually correct. But you got to give me more than that. You got to give me more of how you got there, because you actually don't need to think about the square root stuff particularly. Tell me how you got there. That's the real question. Okay, well, I'll let you think about that. 2 to the I? Oh no. Wait, no, I don't know where you're getting the less than n part. Okay, but like I said, I don't expect you to know that one. So now what we're going to do is we're going to talk about logarithms, and we're going to work our way to understand how to do this problem. But I think first we need to review logarithms, okay? So we shall return to this one, but for those of you who want to play with it, you can in the meantime. And now we're going to talk about logarithms, okay? Because, I mean, this was literally the question from 477, like this version like this with the n squared. And so, I want, if he has that, if Dr. Iwala has that same question next time when you guys take this in a few years from now, then you can, like, nail it, right? So, okay. That's fine. Let's see if once I show you the answer, if that's what you were thinking. So what I'm going to do now is I'm going to write a couple of log rules that are going to help us solve these kind of problems, but also when we get to recurrence relations, okay? So it turns out I don't have these here to copy paste. I have them like on paper. So let me just copy them down. Let's actually start with the square root, since you were talking about that. Maybe this will help you explain stuff. So when you have something to the power of this, what this means is you can do a root of that power and then lift that to an exponent, which is also equal to saying that. And you could also do something like that. I think that will be legit as well. But anyways, going back to logs, if we have the log base of something x, actually, you know what? Before I say that, let's talk a little bit something important about logs, okay? So when I say, like, what is the log of 8, okay? Technically, I'm missing a very important piece of information that I don't usually mention in this class, because I'm making an assumption because it's a computer science class. And that is what base you're using here, right? So if you're using a base of 2, then now you know what I'm talking about. And it turns out that if you're a computer scientist, you're probably going to be using a base of 2. So as a generalization, if you're a CS student and you see a log, more than likely you're dealing with a base of 2. If you are like a physics student or some sort of science student, like natural sciences, or whatever you call them, physics and chemistry and whatnot, you are probably going to be dealing with a base of 10. Okay? Finally, if you're a math major or a math person, what do you think you're going to be dealing with? Base 16, that'd be some hardcore stuff. Natural log, yeah, natural log. Which you usually either say ln or you can say log of n or whatever, but I'll just leave ln, right? Yep, very good. So it's a good, it's kind of, I mean, it's a good rule of thumb. It's obviously not like, you know, there's always the exceptions, but just so you're aware, so whenever I keep saying log, I'm talking about the CS log, okay? So I'm talking about the first one here, because we're CS people, we're not math people, at least during class time, okay? So, okay, it's good to get that out of the way at least once, okay? So you'll probably never hear me again say base 2, but whenever you hear me talking about logarithms, unless I say otherwise, I am going to be talking about base 2, okay? So, math 101 here. What is this equal to, and how do you solve that? What is log of 8 equal to? 3. Very good. So yes, it is indeed equal to 3. Now, for those of you that are extremely rusty, the way you do logs is you can think of it this way. 2 to some power is equal to 8. Okay? So what you're trying to solve here is what this power is, what that exponent is. Okay? That's essentially what a log is. So if I say, what is the log of 16? What you're trying to figure out, and again, base 2, I'm putting it now just because it's the first day, is all you're trying to figure out is, and let's just say it's equal to x, basically 2 to the x is equal to 16, solve for x, right? And so again, this one's going to be 4, okay? Because 2 to the 4 is equal to 2 times 2 times 2 times 2, which is 4 times 4, and that's 16, okay? So, good. I mean, like, that's like the most basic, right? I got to make sure that you're all on the same page here. Otherwise, you're like, what's a logarithm? Like, oh no, this is not good. Okay? So, all right. So now that we're on the same page on that, let us go ahead and look at some properties when working with logarithms, okay? So now we can actually start writing some of these. Because otherwise, if I write these and you don't even remember what a log is, then, you know, you're going to be lost, right? So if we have a log with some base, and that is split as xy, so you can factor that value, this becomes log of bx plus log by. What this is saying is that if you have something like a log of 8, you can split this into log of 4 plus log of 2, okay? And then log of 8 we know is actually 3, right? And what is log of 4? 2 to the what power is 4? 2, right? And 2 to the what power is 2? Just 1. So 2 plus 1 is 3. So there you go. Proof by example, I suppose, right? That's not very good proof, but it's an example at least, okay? So that's one rule. I'll leave the example small. Similarly, you can do the same thing for division or subtracting. So if you can convert whatever you have there into a division of this format, like that, then you just make a subtraction. And I hope this is a little bit intuitive, at least, that works. You know, it's think about like fractions and how you can like factor numbers out of fractions. It's kind of like the same system here. Okay? Now here's a really cool one that you're going to be using a lot. And hint, you might actually use this for the example that I gave earlier. When you have an exponent to this power, like when you have x to some power, and that's what you're trying to solve, this exponent can be brought down, okay? So this becomes n log bx, okay? So what I'm saying is, if you have something like log of 2, and then you have maybe 2 here, so that's the same thing as saying log of 64, right? What I'm saying is that I can literally take this little square part and I can bring it down like that. And it becomes a normal number that you're multiplying times that. And as you remember, log of 8 is 3, so this becomes 2 times 3. Okay? Yeah, okay. And then this is equal to, for a second I was confused, but log of 64 is indeed equal to 6. I was like, is it 6 or 7? But yeah, it is equal to 66, okay? 2 to what power is equal to 66? Remember, it goes 2, 4, 8, 16, 32, 64, 128, right? This is 1, 2, 3, 4, 5, 6, 7. So it is indeed 6, okay? So, yeah. Sorry, for a second I was like, is it 6 or 7? But okay? So that's an example of a very, very, very useful one, okay? Like this might seem like, why would I want to do that? But it's because it makes it easier for you to do the math. You know, instead of trying to remember log of 64, you can remember log of 8, right? But it also will simplify a lot of things, okay? And the hint, this will come in useful with that example that I said earlier with the code, okay? So a very important one. Let's look at another one. Here's some I believe they're called identities. So if you have a log and that of 1, that's just always going to be 0. And if you have the same base as what you're trying to do, that's always going to be equal to 1. Okay? So yeah, I mean, I hope this one's like must be obvious, right? Like a number to what power is equal to the same number, just to the 1, right? And a number to what power is going to just be equal to 1, and that is to the 0 power, okay? So like, I guess remember that 2 to the first power versus 2 to the 0th power, you know, what those are, what that is equal to when it comes to like normal, okay? Like, remember, I guess the one that you might not remember is x to the 0 power, what that is equal to, and x to the first power, you know, is just x, right? But this is the one that like people don't always remember, okay, what that is equal to. So basically that's what these properties are telling you, okay? That it's just equal to 1. Yeah, okay? So moving on, we have, oh yeah, this is kind of cool. I mean, a lot of these, again, hopefully are obvious as I write them, but you know, you might forget them and be like, oh, I should have done that kind of thing. So this one, we have a base, and that same base is the power that we're looking for, and that has something to this. So it's basically saying, like, what is log of 2 to the 10 equal to? And it turns out that that is just equal to 10, or, well, this is just equal to x, and this is just equal to 10. And again, you use one of the other properties that I showed you earlier, because all you're doing is you're bringing this down, like I said earlier, and then it's just 10 times 1. Right? So it just becomes 10 times 1, which is equal to 10. So hopefully that one's another obvious one. Okay? No, it's like frame rate lag. Okay. Yeah, okay, this one I've also seen used, so this is a nice one. So let's say you have a b, and then you have a log b of x. This one, as fancy as it looks like, is just equal to x. Is that alpha on the top? No, it's just an x. These are all x's. I'm just using the same letters over and over again. So b's and x's. A, B, X is my alphabet right now. I guess, and log. This one, it's harder to see that it works, but it does. If you plug in some numbers, 2 log 2 of 8, let's think about what this is doing. This part is just going to be equal to 3, right? And then 2 to the third is equal to 8. So what you'll see is the solution to this is the same thing that you're applying here. And that is how you're getting it. So this is actually like you're basically undoing the log. It's like the inverse of the log. You're like canceling out the logs, okay? It's like when you're dereferencing and then like when you're doing this in C++, like ampersand and asterisk next to each other kind of thing, okay? Yeah, someday I'll post them before like the midterm or the final. Not early. Like I don't want. It's too much work to update them every weekend. But yeah, they'll get posted at some point. I do already have posted the ones from older semesters. I think. I'm not sure. You can also screenshot the video if you need something quickly. But I will be posting this as a PDF later on. Okay. Let's see. Oh, this one's cool. I don't think I've used this one in a while though. But it's still cool to know. So you can flip the base and the number you're looking for. You can like flip them out if you invert it. If you put it 1 divided by. This, if you plug in numbers, will work. For me to explain to you how this happened though, I have to show you the one beneath it. So, which is, if you have something in this format, log a b. You can convert this into log CV over log CA. Okay? So you can change the base like this. And so what the one above it is doing is the C is just the same as the B. So I'm just plugging in the B as a C in here. So if I decide to use like, here I'm just saying like I can take any logarithm and make it a division by arbitrarily picking a random base. But if that base that I pick randomly happens to be B itself, then you can see that log BB it just becomes 1, right? And so now what you end up with is what I had above, like that, which is literally what I have there. So there's your proof of how I came up with the one before it, okay? Maybe I should have shown you this one first, but nah, I just have them in this order, so keep them like that. Yeah. Okay. Moving on, and by the way, all of these are going to come in useful when you do your write-ups, right? Because you're trying to analyze your code and you need some logarithmic thing, so then you just simplify it this way. Finally, this one was one that I actually didn't remember yesterday, and I didn't know how to write it down. When you have the power like that, all this is trying to say is this, which is also equal to log n times log n. I'm putting the parentheses in this one just to not get confused. But yeah, like that, okay? This is not the same thing as log n squared when that is like that. That's the one where you can like take out the power and bring it down here, okay? So while you can do that one in this one, you cannot do in this one. So that's why it's very important to not get them mixed up, okay? So important. And as you saw, this stuff comes back in 477. So make sure you remember it. That's all I have. Yep, that is all I have. Those are all the ones that we're probably going to need. So now that we have seen all these logarithmic properties, let us go back to the problem at hand. This one. So, how to approach this? We already seen that yes, you are correct. that when we just have something that is just like that it is indeed logarithmic. And how did we achieve that? Well, we're trying to solve how quickly this moves around, and it basically is going 2 to the I. And remember, when we're trying to find out, and this is equal to basically n, right? 2 to the n is equal to n. So this just becomes log of I, basically. So that is how we're getting log of n. Maybe I should have flipped the variable names just to not throw you all off. But here, let's flip that. So let's make this an n. Let's just make this an x. And let's make these n's. There, looks pretty now. So now, if I'm doing this, I'm saying that 2 to the n is equal to x. So if I apply the logarithm to it, then it becomes that, right? Log of n is going to be equal, or actually, technically, that's dang it. I flipped them again. I should have left them as I had them, actually. I just flipped that earlier. Yeah, I should have left them as I had them. Because then it would have worked out with using log of n. Apologies. Let me flip them. Control Z. Undoing. One more. There we go. Okay. Much better now. So now, if we have something like this, it's that. There we go. This was good. How we had it there. All I'm trying to do is make the numbers match so that I can use the n for the asymptotic. But yeah, okay? So that's actually how we got this logarithmic thing, okay? Because you see that this becomes 2 to the I, and we know that you can basically rewrite that using logarithms, okay? So, however, when we have something like this, what you want to do, well, actually, before I give you the answer, any last guesses as to what I'm doing, what the little trick to solve this is? Or any guesses as to what the answer might be, the real answer? 2 log n. Why do you think that's the answer? Where's that 2 coming from? The exponent. Yeah. You guys got it. Yep, you got it. Very good. Very, very good indeed. So the best way to think about this, for those of you that haven't gotten it yet, is substitution. Substitute the n times n in this problem with an m. Okay? And then all of a sudden, if you do that simple substitution, easy substitution, piece of cake, right? Easy peasy, lemon squeezy. Then we know that because of what we just did earlier, this basically becomes like 2 to the I is equal to m, and we know that this is equal to log of m, right? And so now that we have that answer, all we do is undo the substitution. So plug it back in. What was m equal to? Well, we said that m was equal to n times n. So just plug that back in. N times n, which we know is the same thing as n squared, right? So we plug in the n squared in there, like that. And now we just bring it down, like that. And that is how you get the proper 2 log n. Okay? So yes, you are all correct. But this is the sort of the step-by-step process of how you came up with that, right? So I like it. It's nice because it makes you think out of the box and reminds you that math is not just about trying to solve a problem, but trying to make it simple to solve before you just like grind it out. So substitution is your friend. Use it. Use it wisely. It's there to help you. See, all this math stuff they taught you is actually useful sometimes. Sometimes, not all times, but sometimes. Okay. So yeah, I like that. I really like that that problem. So props to Dr. Gawali for coming up with it. I mean, maybe he'll leave it in there, and when you take the class, you'll see the exact same problem. I changed the, I think I changed the variable names, but it's literally the same question. So if you see it, give me a shout out in a couple of years and be like, hey, I remember this. But yes, it literally came out from his home. So I liked it. I liked it a lot. Okay. So we have done a logarithmic one. We've done an exponential. Actually, we haven't really done an exponential one. Yeah, I guess I can show you that. I mean, it's somewhat trivial, but let's just show it to you anyways. Let's do one exponential one. So that would look like for int I is equal to 0, I is less than how do I make it exponential? Well, if I do something like this, yeah, I think that'll cut it. Yeah, I think that's technically, that's technically exponential. Let's just do the substitution again and see. So let's just substitute m for that. So this would be O of m, right? But then if we plug it in, it becomes O of 2 of n. So yeah, there you go. Substitution again to the rescue. So yes, this is indeed exponential. So yep, that's exponential for you. Okay. Be ready to wait a long time for that code to finish. So yeah. Okay, does anyone have any questions or any particular examples that they might want to play with? Otherwise, your homework assignment is going to be just this. You are going to be having four pieces of code, of which you've pretty much seen almost exact examples, because you can only do so many different examples for this. And then you're going to analyze the runtime, but you're also going to code it to like prove. So like right now, you know, I've been showing you this, but I haven't really like run the code, right? And so what I want you to do is to run the code and prove yourself that it is actually running this many times. Because that is another way that you can measure things. If you're just completely lost on what a piece of code's runtime complexity is, like, and this is something that I told my friend when taking 477, I said like, hey, if you're stuck and you really can't figure out what the time complexity of a piece of code is, all you gotta do is plug in numbers. Plug in a couple of numbers in, like plug in n. So like, let's say you have a thing like this. Like let's say you have a n log n, and you're trying to compare this and see if it grows faster than n log n times log n. And somebody asks you like, which one runs faster? And you just don't know. Okay? Well, we'll just plug in some numbers and see how it works. Like plug in like a small number like 5. Well, actually, another trick, if you're dealing with logarithms, plug in numbers that have easy logarithm results, like 8, like powers of 2. Don't plug in like 5, because then you're like, oh crap, what is log of 5? And you gotta like use a calculator for that, okay? But if you got easy numbers, like if you pick an 8 or a 16, then you can do that. So let's do that. Let's start with the 8. So let's say we're gonna do n is equal to 8 for one of them, and then maybe for another one you're gonna do 64, and then maybe 128, okay? And then you just plug them in and see. So you're like, okay, well, this is going to be 8 times, and then if you plug in 8, that's a 3, so 8 times 3 for the first example. For the second one, it's going to be 6, and then for the third one, it's going to be 7. So the answers to this is 8 times 3 is 24, right? Yeah. 8 times 6 is 48, and then 8 times 7 is 54, right? Wait, 54 or 56? Hold on, that doesn't seem right. 56. Yeah. Okay. Math. And then over here is going to be the same thing, but you're multiplying. I mean, it already should be obvious by now, but like you're multiplying another 3 there, right? And in the second one, you're multiplying another 6, and this one another 7. So you can already see that this is going to be much, much, much bigger, right? 24 times 3 is going to be 75 minus 3, 72. 48 times 6 is going to be approximately 300 minus like 12, so something like 290 something ish. You can already see that this is way like, it's way bigger, right? So there you go. Then you can be like, this has a faster growth rate, okay? So let me plug in those numbers so I can fill in the right numbers there. 8 times 6 times 6 is 288. That's close enough. So I was supposed to do minus 12. Oh yeah, that is 300 minus 12. I should have trusted myself. And then the other one is 392. Okay? And then, okay, so anyways, now we have a couple. Great. So we have a couple to play around with. So, or actually we just have one. Right? Because you were just saying that log n squared becomes 2 log n squared. Yeah, okay. So we have one. Are you sure that's not from the homework though? Because if you feel, yeah, are you trying to trick me? Let me check, make sure it's not from the homework though. So I don't want to give you the answer to the homework then. Where's the fun in that? Let's see. Oh no, man, I can't believe it. I didn't even give you in the homework any like logarithmic ones. I'm so sad. Very sad. Okay. And yeah, you're right. Okay. But I really, since it hasn't opened, maybe I should make it harder. I don't think there's any logarithmic examples in the homework, and I feel like that's injustice to you guys. But so maybe I'll make it harder. Okay. Let's do it though. I is less than n. I is equal. But I mean, come on, it's not that hard to do the log ones. Like, there wasn't the homework. Like, I hope I don't know. I'm sad about that. Int j is equal to I. J is less than n. J is equal to j times j. Make it impossible. Kick these out. Okay, nice memes. Okay. All right, I think I copied it right. Let me know if I didn't. So, okay. So first of all, forget about the outer loop and think about the inner loop, because that's the best way to kind of look at it first. Otherwise you just get confused. So in the first time this runs, it seems like I is going to be equal to 2. Okay? So if j is equal to 2. So if j is equal to 2, that first iteration, j is going to go from 2 all the way to n, but it's not increasing linearly, it's doubling each time, right? So in this case, you know, before we had like a 2 to the I kind of thing, here we have like a j to the j, okay? And that's going to be equal eventually to our n. So, okay, that's really, really nasty. It's going to finish really fast. In fact, it's going to be finished probably logarithmic time, but I'm just trying to see if it goes even faster than logarithmic time. It's a logarithmic time, but like it's finishing with the same base. So one times one. Is it ever going to finish? Okay, it is going to finish because it starts at 2. I was thinking it wouldn't finish, and I was like, is it going to finish? But yeah, it's going to go from, so the first time it's going to go 2 times 2, which is equal to 4. And then the next time around, it's going to be 3, or actually it gets increased. So 4 times 4. Okay, so more than likely, I would claim that it's logarithmic or less than logarithmic for the internal one. So let's just go with logarithmic for now. And then the outer one is going to also be logarithmic. So this is probably something like that. Is what I would guess would be the case. So a log n. You write that as this. That's what I think this is going to be. However, Maybe I should put this one in the homework, and then you guys can check it and see if I'm right or wrong by actually running it. Like just plug in the 2 for loops and then just run it, and then see if it's actually close to log n. There's probably some constants associated with this in here, like a 2 or something, but I'm just ignoring that without like analyzing it carefully. Okay, so that's what I think, unless you know the actual answer. So this brings up a good point. It's a good idea to list a couple of time complexities so you can see the growth rate for all of them. Okay, and I have a couple here. Because I do like to put this into tests as questions, and I was yet another homework from the 477 I saw was asking the exact same question, so definitely want to cover this. So let's talk about growth rate, okay? Because like this log n, you might be asking like, is that faster or slower? Of course, like I said, you can plug them in and figure out, but it's also good to just have a nice list of them. So when you think about asymptotic complexities, you know, the bigger the number means that it is the fastest to grow, or in the sense that it gets the slowest quickly, okay? So fastest to slow down. You gotta make sure you don't mix up these terms, okay? So if I say, well, we got a code that runs in quadratic and a code that runs in linear, this code is faster, right? Faster in terms of like to finish. However, this code is faster in terms of growth rate, okay? Because it grows faster in the sense that like it needs more work to be able to complete something when n is bigger, so it has a higher growth rate, okay? So make sure you don't mix those up, all right? So let me give you a list of a couple of them. So we got the slowest possible code, also known as the fastest growth rate, is going to be that. It's called factorial. If you got an algorithm that's factorial, you have a problem, because that thing is not going to finish any day. Like you're probably going to age, and it will still be like on step 5 or something, okay? So that's really bad. Then, of course, you have your exponential stuff. So like 2 to the n, whatnot. And of course, within those, 3 to the n will be even slower, right? Or faster growth rate. Then you have your polynomial times, like 4, 3, 3 halves, you know, something like that, I suppose. Well, actually, let's do a bigger one, just because I don't want to mix them up later. Let's do like 4/3. No, let's leave fractions out of this for now. Okay, I'll come back to the fractions in a minute. Anyways, after those, you get your n log n that we saw, the linear rhythmic thing. Then you have something like what we just saw, like that. But actually, what we saw was without the n part component to it. Then you have your n. Then you have log n, but I'm leaving a space there. Then you have a constant time. So like 73 or whatever. Then you have 1, and then you have your 0, right? So this leaves square root, which is equal to 1/2. So let me show you the proof, the pseudo proof of how these two are actually equal. Okay? So n to the 1/2, right? Let's look back at our log properties. In our log properties, we said that let's see, which one can we use from here? Well, actually, we're kind of going from this to log. So really what we want to do here is we want to apply the log to this, right? To see what it would look like. And so if you do something like this, then we know that you could take out the 1/2, right? So this would become like that, right? If you apply that. But then, technically speaking, if we do that, we have to apply it to the other side, right? To whatever answer we're doing. So, what's the proof for this? I'm trying to remember it. Actually, you know what? How about this? Let us take log of n and convert it into the square root of n. That'll be much easier to do, okay? So, let's go ahead and by the way, we can add constants. We just can't add factors of n. So, if I divide this by 2, or take it to the 1/2 like that. Yeah. Okay. We can do. I know what we can do. Okay, I know what we can do. We can do this one. We have the log AB is equal to 1 over log BA, right? So we can apply this once we get it into the right format. Or we can actually even, or let's use the one that we said that we explained for that one. So we can go with log CB and log CA, okay? So what we're going to do is we're going to take our log n and we're going to apply it like this, okay? But something that can cancel the log part out of it, because that's what we're trying to do here. So we're going to say log to the n power, okay? So we're going to say log n. Maybe this will work. I don't know if it's going to work. I haven't done this in like proof in a long time, so I forgot it. So if we do that, then it means that the bottom part of that, which is a 2, should go here. And then the top part of that, which is the n, should go here, okay? I think this will get us somewhere. All right, so now we know that log n is just going to be 1. And so now we have log n true. Oof. Is that going to help us or make it worse? I don't remember this being this complicated. Yeah, I don't think we're going the right route with this. Let us Google how they did it. Raise the log to a base. Raise the log to a base. But they have to raise it to the side. Let's just find the solution. Square root and log n equality. Okay. So it claims that log n is equal to 2 log square root of n. Oh yeah. That was way simpler than we were trying to do it. Okay. I'm glad we Googled it instead of trying to like reinvent the wheel here. Remember that square root of n can be written as 1/2, right? So all you're doing is taking this times this, bringing this up, which means 2 times 1/2, which is just equal to 1. So then you get log n. So yeah. Okay. Here, I'll post the link where I found that. You all can read it later. Stack Overflow. So, yep. But anyways, essentially, whenever you see both of these, you can basically say they're the same thing because of that. Okay? So, yep. Oh yeah, there's l'hospital or hôpital because it's French rule. Sometimes they go over that in 302s, but I don't like going over that. I know Jimmy does in his 302, but I prefer recurrence relation stuff. But I'd encourage you to read about that if you're curious. They mentioned that in the explanation, so you know, check that out on your own time if you prefer. Okay, but I'm not gonna cover it in the class. Maybe they'll do it in 477. Yeah, or math classes might cover it too. So yeah, okay. So anyways, that's your time complexities that you might experience, and you know, you make sure that you know. But if you don't, always just plug it in to see if you're unsure, if you're like, oh snap, which of these goes first, you know, between these two in a test or something. Plug in numbers and just figure it out. Like literally just plug in some numbers. And again, pick numbers that are easy to take the log of so that you don't like get stuck trying to take the log of 5 for like 2 hours or something by hand. But you have a calculator too. So yeah. Okay. That's it. So now we are going to change topics. Scary stuff for the remainder of this. All right, we have the massive theorem. We have a lot. I don't know if last time around I covered the massive theorem. I don't know if we'll really cover it this time around. I'll maybe just make you watch that video if you're interested in that. Okay, so okay. See if there's anything else in here. Oh, I guess this is a good example that will lead into the recurrence relations, just so you get an idea of like what things might look like. Let's suppose that I had code like this. Okay. And this code is running in parallel. Okay. So put a bunch of semicolons there. Okay. So we know that because it runs in parallel, you would add it together, right? So you'd end up saying n divided by 2 plus 3n divided by 2 plus 2n, right? So you would just basically combine all of that and get what you get out of this. Let's see. 4n, I think you get out of this. Yeah, 4n. Yep. Okay. And so you know that you can just combine and add common terms, right? Very good. Okay. So I just had that as a possible example there. So now that you know that you can add common terms, let's talk about a very, very scary topic for this class. It's going to be the hardest topic of the class. And that's recurrence relations. And this is something else that you can put in your write-up. You can figure out these recurrence relations when you're figuring out asymptotic complexity. So what are recurrence relations? Well, recurrence relations are used to determine the runtime of a recursive program. And by the way, the recurrence relations themselves are actually recursive. So let's think about for a second. Whenever you're dealing with iterative code with for loops and everything, what I've shown you is good enough. Like you can, you see some code that's like loops, nested, whatever, you're good to go, right? However, if you notice, neither in the assignment when you get it at 9 or in the examples I've given you so far, did I give you anything that's recursive, right? And so it becomes a pain trying to figure out the asymptotic complexity of recursive code. There's just no way around that. It sucks. You can't really do what I've shown you so far for recursive code. Like it just does not really work out. You can try for very basic baby programs. You can try, but it's not really gonna work out for anything more than like a simple toy example. And so we have to do a completely different way of analyzing the asymptotic complexity of something that's recursive. And unfortunately, it's not easy because that solution itself involves more recursion. So, and as we all know, recursion is not something trivial, at least when you're first learning programming. So, let us show you what that looks like. And I know we only have 10 minutes left, so we're going to kind of pick this up next week. But let's at least throw some stuff in so that you can start to think about it. Okay? So, let me, how to start giving you a recurrence relation. Let me start by giving you an example. I have some examples here that are simple, but I don't want to get an example that's going to be like super hard, okay? I think this one will be good. This one was going to take us like half an hour to do, so not really good one. So let me show you what a recurrence relation looks like, okay? This here is a recurrence relation. This is saying, basically, that each step in a process of a recursive function is going to reduce the number of steps left by 1, as you can see here, t of n minus 1. And in the process of reducing that step by 1, you're adding 2 operations, 2 seconds, whatever, to the time it takes to figure this out. Okay? And so the end game here is to figure out, okay, if all of these run, how long is this going to take? So let's just try and plug in like a number for n. Let's suppose that n was equal to 3. Okay? The way that you would sort of plug this in manually is you would say, okay, if I'm trying to figure out how long this is going to take to run, you start out by saying t of 3, because n is equal to 3, is going to be equal to however the 3 minus 1 step takes plus 2. Okay? So what I'm telling you is, okay, if you're asking me like, okay, when n is equal to 3, how long does my program take to run? And you're like, well, it's going to take the amount of time it takes to run a program with n equal to 2 plus 2 seconds. Okay? So the next question you ask is, great, awesome. How long does it take to run a program with with step 2 though? And you're like, well, if you want to figure out how long a program takes to run for a step of 2, you apply it to the same formula that we had above, which ends up saying that it is equal to t of 2 minus 1 plus another 2. So this becomes 1 right here, right? So the answer is, okay, a program that has an n equal to 2 will take however long a program that takes 1 step does, plus another 2 seconds per se. Okay? Great. What happens now with t of 1? Well, that's going to take the same time that a program of t of 0 steps takes, plus 2. And so you could go on forever, right? But remember, when you're dealing with recursion, you need a base case, right? You need a base case to stop the recursion. The same applies when you're dealing with recurrence relations. You need a base case. Now, if a base case is not given to you, it's assumed that when you get something of steps with 0 steps like this, that's the end of it. Okay? And so when you see something like a t of 0, that is going to be your base case. Although sometimes t of 1 can be used too. It really depends on the problem. And it's usually going to be equal to some arbitrary number like a 0 or a 1 or whatever it is, okay? So, again, when you see t of 0, that's your base case, and that is representing the time to solve 0 or 1 problems, okay? And when you see t of n, that is the time to solve a problem of size n, or of n steps per se, okay? And that's your recursive case. So going back to our problem. If let's say that we have a base case where t of 1 is equal to 1. Okay, that's our base case. If we know that's the base case, then we can substitute and plug it in, right? We can say, well, let me actually move this down so you can see it better. You can say, all right, let me plug this in. So that means that this goes away. I'm going to put in a 1, which means that t of 2 is equal to 3, which means that I can take this away and plug in a 3, which means that t of 3 itself is equal to 5, which means that I can take this. Oh, wait. I might have gone too fast and screw something up. Let me make sure I didn't screw up things. Okay. So t of 1 is equal to 1. So this is equal to 1 here. That's equal to 3. T of 2 is equal to 3. So I guess I didn't go too fast, which is equal to 5. And then that's it, t of 3. Yeah, because that's what we were trying to solve initially. It's just that I pasted it twice, because it's the same thing here. So yeah. The answer to your question is a program that takes 3 steps, or n is equal to 3, is going to take 5. Okay? So that's great if you're trying to solve it for a specific number, right? In this case, for 3. However, what if you're trying to solve the general case when t is equal to n? You're trying to see what is the asymptotic complexity of that. Because remember, we want to have the formula. We don't have a single answer for like a single case. No, we want to have the general solution. That's what you're going to do with recurrence relations. You're going to take that, and we're going to solve it using some math, including the stuff with the logarithms that I showed you for the ones that have logs in them. And we're ultimately going to come up with some time complexity in big O, or theta, whatever. Okay? That is what we're going to be doing next Wednesday, because Monday is Labor Day. But at least this kind of introduces you to what we're going to be doing next. And it's a hard topic because recurrence relations tends to be something that people really screw up, and there's a lot of like okay, you just have to find the pattern kind of thing. Like you start seeing things and you sort of pick up on the pattern and then you solve it. There's no like simple way of solving it. However, master theorem kind of is a simple way of solving it, which I do like to show. I just don't know if I have time to show it this time around. But if I don't, I have it on my videos from other semesters. But or you can just Google it. So, because the master theorem is like a shortcut for solving some recurrent relations. Not all of them, but some of them. And if not, 477, they will 100% go over it. But yeah, that's all I have for you today. So today was an interesting day because there was a lot of interesting random math. But the reason I'm showing it to you all is because you will be using this in your write-ups for each program. This is the stuff you're going to be doing. You're going to be analyzing the code, and that's going to be what assignment 2 is about. It'll be kind of like a practice run of that, where you're just doing that. Okay. So yeah, the Fibonacci sequence is actually literally what this is. Recurrence relation is actually this, or it could be at least, because it's going n minus 1 and minus 2. So the Fibonacci could, like this recurrence relation could represent a program that can write the Fibonacci sequence, assuming that each of those numbers took 2 of these steps. So yeah, that is one example. Great. Well, since it is Wednesday, I wish you all to have a good weekend. And make sure you get the second assignment done. And even if you don't finish the first assignment before the due date, remember you have 24 hours to finish it with a deduction. But even then, you want to finish it because other assignments will require it, or otherwise you'll be stuck. So make sure you finish it, all right? Enjoy the long weekend, though. Get some good rest, because next week will be, that one class that we'll have on Wednesday is going to be intense. So we want to make sure we're rested for it. Both you and I. So, all right, I'll see you all later. Thanks for coming. Appreciate it. Take care and stay safe.